So I like to start the explanation about this proton-led run that will take place next year by a bit of history, telling or explaining you why we have this kind of collisions today. Although this was not the baseline at LHC, in fact they are considered, these proton-led collisions, like a future upgrade of LHC. The reality is that today we are upgrading the machine well beforehand as it was supposed. And this is thanks to the visionary spirit of John Jowett, who is the accelerator physicist leading in this adventure, that in the background he was working out this idea for many years until in 2011 the ALICE experiment requested these collisions, followed by the success of the lead-lead collisions that took place during this year. So at that time it started to be discussed among the physicist community, and John quickly put together a nice group of people, a team that was working together in order to address the feasibility of these collisions in LHC, because it was for the first time a new way of running the machine. And as you know, it's not anymore the same type of particles, protons against protons or lead against lead, is protons against lead. And this implied to change several things in the accelerator side, so it implies some technological challenges. The first feasibility test of protons against lead took place the 31st of October in 2011. And this was our first success, because we could not only have a series of proton bunches running in the machine together with a few lead bunches, and we proved that at injection energy this is a possibility. But we as well put two proton bunches against two ion bunches, and we ramped them, and we put them, both of them at flat top, and we could do what we call the cogging in order to have the two frequencies locked together. We found, of course, various problems, because this is a new way of running LHC. It was not done before, and it was the first time a machine with the same magnetic field for both beams was running two different particles together. We know at ESR it was done before, but they had two different magnetic fields, two different beam pipes for the two species, and at REYES, at the heavy ion, relativistic heavy ion collider, they also have two different magnetic fields. But in LHC we have the same magnetic field, so the two-in-one magnet structure, which is fixing the magnetic field for both beams. So this is not free anymore, and this is why we have to work with the RF system, the radio frequency. There is a fundamental difference with respect to colliding proton-proton or lead-lead. For this kind of beams, the encounters in the straight sections where the beam pipe is common to both beams, they are always happening at the same position. These are long-range encounters. That is not only in the IP, but at both sides of the IP, the two beams meet each other. Not frontally, not head-on, because there is a crossing angle. But with proton-lead, because the revolution frequency is different, these long-range encounters don't happen always at the same position. They are moving all the time. In fact, they move with a speed of 1,734 meters per second. So this is a problem in REYES actually. This was a problem in ISR, the intersecting storage range here at CERN. And this is what was called the knockout resonances. The fact that the beam is meeting the other beam at different frequencies in different positions was exciting extra resonances in the beam and was making the beam explode and lost. and the beam was lost. So why is it an unprecedented way of running LHC? And it's because we have protons and running against ions, and what is the main difference is that the charge and the mass is different. So the velocity is different for these two types of beam. And as I said before, we have to live in the same magnetic field. So we don't have this degree of freedom as Rick has. Therefore, we have to find another degree of freedom, which is the radio frequency system. And this is the key point in LHC that allows us to do this kind of operation. So when we put ions and protons at injection, they are running in different radio frequencies because it depends on the charge and on the mass. In fact, at injection there is a difference of 5 kilohertz of a frequency difference of 5 kilohertz, but this frequency difference is getting reduced as we ramp the beams because the ions becomes more faster, more relativistic. So when we are at flat tops today for TeV, the frequency difference is of the order of 70 hertz. So because they have their own frequency, both beams are running at the reference orbit, which is placed more or less at the center of the magnetic elements. Once they are at flat top, we have to put them in the same frequency because otherwise they will not be able to see each other ever. And this is what we call the rephasing and cogging process, which is the first time was done in LHC as well, when we did the pilot run. So this mechanism consists on moving the buckets, the RF buckets, all around the machine until bucket number 1 of beam 1 collides with bucket number 1 of beam 2 at a given IP, which for us is always IP1, the reference. So when we went there, the difference between these two buckets was of 9 kilometers. They were 9 kilometers apart. So with an RF gymnastic that took at that time 30 minutes, because it was the first time that it was done, so you always learn. Now, of course, it's improved. Took us 30 minutes to move these two buckets to meet each other at IP1. And once this was done, the beams that at that time were still separated were collapsed in the vertical and in the horizontal plane, and then at that moment we could declare the collisions at the experiments. We were running protons against protons and lead against lead, and we never had ask ourselves the question, what would happen if you try to inject a proton beam into a ring in LHC which is set up for ions? We know the frequencies are different, so can we damage the machine? So we had to ask ourselves these questions and put in place an interlock system which prevents that we accidentally inject protons in the ring set up for ions and vice versa. So it's easy to calculate that if you have a ring in SPS which is set up for ions and you try to inject protons in, there is an energy error of 1.3%. Okay, this is at the limit of the acceptance in SPS. The beam could hardly survive, but it could survive in SPS, a proton beam with a reference for ions. But then this beam has to go out from SPS and enter the transfer line into LHC. So what happens next? The energy error, the tolerance in energy error in the transfer line is only 0.4%. So the beam will not make through. It will die in the transfer line, but with huge losses. So we thought, okay, we have to avoid that we are able to inject protons in a transfer line set up for ions and vice versa. So this was one of the things we had to set up and put in place. Another thing is that the proton beam is running with a range in intensities which can be very different to the ion beam. Therefore, all the beam instrumentation has to be set up differently for each beam according to the intensity. And this is today one of the problems we are facing, that the interlock BPMs, beam position monitors in 0.6, they are not yet set up properly for low proton beam intensity, and this is why we are losing our beams. The expectations for the run are to collect of the order of 6 to 7 inverse picobar, which implies that for ALICE we hope to deliver a luminosity of the order of 10 to the 29 instantaneous luminosity. Of course, respecting that we should not go beyond 0.05 of pile-up events. The operation will have 4 parts. We will run proton against lead, proton in beam 1, lead in beam 2. Then we will flip the polarity of the ALICE dipole to get more or less the same amount of data. And then through the run, more or less at the middle, we will switch species and we will put lead in beam 1 and proton in beam 2, and again halfway switch polarity of the dipole ALICE spectrometer. So what will be decided during the commissioning, during the first week of commissioning, is the beta star, so the value of the beta star, the betatron function at the interaction point at the experiments. Several values are considered. The lowest one will be 0.8 meters for ALICE, CMS and ATLAS. LHC will stay around 2 meters. And as well, what will be decided during the first commissioning week is the intensity of the proton beam. Of course, the higher the intensity, the better, because we can give more luminosity. But all these have to be still established in order to define once for all the parameters for the run, and then define the instantaneous luminosity.